morning, everyone. Um, Scale. So yeah, the title is Size Matters. A little bit of context for myself. I One of my first jobs in the space was actually at Chainalysis. This was between 2017 and 18. And now, as introduced, I work on goods for the public, particularly two protocols, the Namada and the Nama protocols. So why am I giving this talk? It's actually been a lot of years since I worked ever since. But actually privacy still sucks. Is basically inexistent right now. But something I've realized after working and following out all the research and knowledge proofs is that actually very few understand why privacy sucks and in the practical manner. So this is why I structured this talk in two parts. So the first part is just sharing my chain analyst point of view, and with the hopes that you can take this into account, this perspective into account, if you're actually building privacy-preserving tech for the users. And the second part is about two approaches in the design of protocols that we are taking. Part of it has been motivated by my previous experience. Oh, also this talk is not that technical, so expect a lot of diagrams and memes coming along. So first part, thinking like a chain analyst. So first of all, chain analysts are not detectives. So what this means is that detectives actually look for 100% confidence, and they look about the really specifics of the individuals they're trying to find. And chain analysts actually don't care about 100% accuracy. They do care about having more coverage over, for example, all the transactions on a network like Bitcoin or Ethereum. I don't necessarily care about a real-world entity. And the success metrics of how good the work is depends on who the analysis is for. And some chain analysts do it for fun. There's been some interesting stuff out there in open source world. Most of it for science, but most actually do it for profit. And we have centralized entities like chain analysis, and now we have decentralized entities or applications that basically create this entire market for on-chain data, like Arkham. So yeah, chain analysts get paid a lot of money for helping others make money, compliance, or helping law enforcement with their investigations. Okay, so that was the motivations of a chain analyst. So working like a chain analyst, what do they actually do? And it's really simple. So they take a really large anonymity set. So think of, for example, all the transactions and accounts on Bitcoin or in Ethereum, and the goal is to turn into like a small anonymity set. There are primarily two large groups of methods that you can apply in these cases. The broadly applied one is passive methods, which means that you just take the data, you kind of like just observing the data that is being produced by people who are actually using these chains. The methods here actually just like statistics, transaction graph analysis, and heuristics. But what's actually, and they're not very sophisticated a lot of times, but often they are more than enough to de-anonymize big parts of on-chain activity. And this is actually because even today, the anonymity sets across privacy-preserving systems like Tornado Cash and cryptocurrency protocols is still really, really small. So even applying just passive methods leads to really good results. Like this is in the case of an analysis done on Tornado Cash in a set of 2019, so it's earlier stage Tornado Cash. But just by applying passive methods, they actually reduced the anonymity set of ETH Tornado Cash, the largest used red asset, by like 60%. Just to show you how just doing some statistics, you can actually de-anonymize a big part of a major privacy-preserving application on Ethereum. The other large group is active methods. Active methods, unlike passive methods, are where you as a chain analyst actually interact with the systems with the purpose of finding out more information that you wouldn't by just observing. And some of them are really simple. It's just like you can interact with the systems, right? So you basically, for example, if you want to monitor what exchanges are doing, the best thing you can do is to actually deposit amounts of money in there and then monitor and see how the flow of funds go. And like actually, this is the case. Like, I think decentralized systems are truly decentralized or cannot discriminate anyone from using them. And this actually includes people who do it for the purpose of performing chain analytics. So one of my favorite active methods is the non-gift attack. And this is particularly interesting when you're trying to de-anonymize users of zero-knowledge proofs. So this is in the case of the shielded pool of the Zcash protocol that uses zk snarks, but this applies to any other system that uses some kind of zero-knowledge proofs. And then the way this works is that simply you dust these accounts, these addresses, before they enter the shielded pool with like really lower digit but unique sequence of funds, and then you wait until they exit, and then when they exit, the lower amount of digits are likely to change, so you just can basically correlate those two. And actually, the survivability of this fingerprint is really high, and this is probably because people are still used to the behavior of we use shielded pools as mixers, so like enter and then exit immediately, and there's just very little activity in between that can really remove the fingerprint and the default behavior wallets. So yeah, and you can actually get, as a chain analyst, even better results when you combine on-chain versus with off-chain data. Off-chain data is, like the previous talk, IP addresses, like Twitter profiles, pasting, sharing your addresses on the internet and being crawled. Like combining all this information actually leads to even better results. So to summarize, a chain analyst's job is to basically take large learning data set, apply active, combine it with passive beta sometimes, and then if you can even combine it later on with OSINT or like off-chain data, you get to, a lot of times, even a smaller learning data set. Something interesting that has happened because we now have more expressive layer ones like Ethereum smart contract platforms, is that compared to the cryptocurrency protocols where everything was compressed into a transaction, actually nowadays with smart contract platforms and account-based models, we actually have more qualitative data on chain. So in the case of Bitcoin, you had to do more work to determine, okay, this is a transaction, but what is this transaction for, right? Like what is the activity of this entity or this group of entities? But in the case of Ethereum, this is easier because applications, smart contracts do not have a functional privacy. So you can like read what the logic is and then therefore know what activity is. So in the case of Ethereum, and this is combined with like OSINT, like people using Twitter, NFTs of Twitter profiles makes it even easier. So like in the case of Ethereum, you can do like some statistics and everything, but in the end, the killer is that you like link it directly to real world entities in some cases. So yeah, one doesn't anonymize Ethereum, then Ethereum doesn't anonymize itself, just making, just stressing on like this actually more qualitative data on Ethereum that in only transaction-based systems. And actually that makes it easier to de-anonymize. But you say, okay, we have made so many advancements on zero-knowledge proofs, and this is true. Actually, this is one of the side of technology that is like most exciting. But so first reminder is that zero-knowledge proofs are not necessarily for privacy. So that a system uses zero-knowledge proofs not necessarily means that you get privacy. So you can actually, a big part of applications of zero-knowledge proofs are a lot more in the domain of data succinctness and efficient verification. So there are two classes that I've seen, like zk AVMs. It's about you have off-chain compute and verify it on-chain. This is like in the case, the work of Polygon Hermes or Scroll, and zk bridges. So like more efficient like clients. I think the talk after me is actually about zk bridges. So you can use zero-knowledge proofs, so not necessarily that is for privacy. But of course, you can use zero-knowledge proofs for privacy. And then here I want to differentiate between two parts. Like one part is data privacy as like information about the activity is being hidden or revealed. And function privacy is a lot more about the logic of the program being private itself. So examples of data privacy are shielded transactions, Zcash, Nemata, Tenor Cash to an extent, and Zk Money, just like protocol from Aztec back then. And the functional privacy is where the logic of the, let's say, smart contract or program in itself is hidden. And there are different constructions like the family of ZC versus ZC. And then we're also working on a new architecture for more intent-centric, with an intent-centric design with Taiga. That actually provides both. So yeah, data privacy and shielded transactions versus chain analysis. So people think that, okay, if you're using knowledge proofs, then there's just like no data being leaked. This is actually not true. The transaction graph of shielded to shielded transactions is hidden. But this table represents, highlighted in red, how much data is actually leaked, even when you interact with systems that support shielded transactions and knowledge proofs. And you can see that even in the case of shielded transactions, the data that is being leaked, or you can infer from monitoring the shielded set, just like from outside, is non-zero. So this is just like highlight that even in this case, you can de-anonymize a fair bit of the activity. So, and the reflection of this is that most of the data is leaked when our transparent address is involved, especially when you are like transparent, obviously. But when you're shielding and unshielding, that's when you are necessarily involved with transparent address. But the least data is leaked when interactions remain within the shielded set. Like in the previous table, there is some data, but if you maximize the amount of the interactions within the shielded set, then the data that is leaked is actually the minimum that you can get. And in the case of Zcash, which is at the moment the largest anonymity set using Zcash larks with a shielded set, Zcash sapling, you can still do a lot to anonymize them. This is the case for example, the fee, the wallet behavior here sets like a default fee, and that actually allows you to correlate a lot of like transactions going shielding and unshielded transactions. And sometimes you are forced to unshield. So this is the case where, in the case of Zcash, they had to upgrade the circuit, they had to upgrade the pools, and they had to ask people to actually migrate over. So that forces you to actually, so let's say from Sprout to Sapling, you actually have to unshield. And then they did the latest upgrade where they actually removed the need for the trusted setup. But sadly, most of the users actually remained in the Sapling shielded set. And just to show you how much you can do with all this data, and this is specifically about Zcash sapling, there was this study in 2020 that was done, and they covered 95% of the coverage deposits into the shielded set, and plus 87% of the withdrawals, just using passive, active, and a little bit of OSINT. So yeah, now we are in a world where it's no longer just like maximalism into one protocol, into one coin. It's like most users here nowadays are usually holding different assets and interacting with systems across domains, right? So the majority of users nowadays is multi-chain, and that opens the question of like privacy across chains. And the answer to that is that the cross-chain transfer in a regular transfer to between Bitcoin or Ethereum is the same. It's a public transaction. And that just makes it really easy. It just makes it really easy for people to de-anonymize. And in the case of what we're working on, right, which is also something that supports zero-knowledge proofs, even in this case, if you were to interact with another system that is transparent, we will have to rely on bridges. And then in this case, we're working on an Ethereum bridge. But this transaction that goes across domains is the same when it comes to revealing information, is a transparent transaction. This is via IBC, which is another interoperability protocol. Even if you wanted to do have two systems to support natively privacy like shielded sets, because of how the bridges are constructed, you will have to necessarily unshield or interact with transparent addresses. So this information could actually be linked by chain analysts. The solution to this would be actually come with a design of private bridges that would remove the transactional graph between systems, especially if they support natively privacy, But this is still an open research problem of research private bridges and private IBC. So the TLDR of the state of affairs is that people who want to break privacy have a really easy time, and people who want privacy have a real hard time. So how do we turn the tables around? So question for the audience, which shielded set do you think is the hardest to anonymize? And the only difference between A, B, and C, and D is actually the size of the shielded set. D? Yeah. So I would say it was easy to get consensus around like between A and D, like D is significantly harder to anonymize. Between B and C and D, like it's harder to tell. But size definitely matters for anonymity sets. So the larger the shielded set, the stronger the privacy guarantees you can get. And there are different ways to actually maximize on-chain privacy. I'm actually really excited to see next year there will be many more systems, infrastructure layers and applications going live that actually focus on privacy. So an approach that we are taking is in an architecture that is still blockchain-centric and transaction-centric, is that we're taking a shielded pool and then making it multi-asset. So this, the goal that it has is that anonymity sets are actually really small because they are fragmented by protocol, by currency. For example, if you want to get privacy, you have to use specific currency or you have to go to a specific platform. So a technique that we can do with the MSP circuit is that we can make all assets independent of the type, being fungible, non-fungible, independent of the domain where they come from, share one anonymity set. If people who, and then this allows us to actually remove the upper boundary of the size of the anonymity set. And ideally, something that you actually could do is, with the multi-asset shielded set, is that all assets across all chains can be part of this anonymity set. That allows to go from the shielded transactions from one asset like Z or XMR to like one unified shielded set. And then as we have seen more real world assets going on chain, we can actually have all of them even increase the size of the set. So like one shielded set for all assets in the world. So that's one thing you can do, remove the fragmentation of privacy sets. So instead of small pockets across domains, we have just one. If in the end, everyone what they want is the same with just privacy. So another approach is, which I haven't seen that much, is, so the hardest thing about privacy is like really how can you get to enough of an anonymity set for it to be practically private, right? So you can actually apply experiment with token economics, as in this case, what we're creating is a mechanism through the circuit where users that contribute effectively to privacy, not just spamming, but like moving assets into the shielded set, maintaining them in there, get actually rewarded by the protocol for contributing to privacy. And this is done by an extension of the MSP circuit. This is the convert circuit. It is specified in the protocol specs, and I think the previous slide showed the repository of the circuit, which also includes the convert circuit. So this is another approach that I would hope to see more experimentation with. How can we incentivize more people to actually use privacy over transparent transactions? A reminder of a takeaway. So the least data is leaked when interactions remain within the shielded set. How can we keep people in the shielded set, or like at least if they leave, have them come back? And the answer to that is you have to enable more interactions within the shielded set. I think a major problem is that people use privacy-preserving systems as mixers, which is like in and out, but not really using the features in there. So you can actually enable more features. In the case of the multi-basket shielded set, that's still not locked. So you can actually do any applications that require just some payments. You can do them directly on that. But another approach we're taking is enable something what we call shielded actions. So think of it as the multi-asset shielded set is more of an anonymity front end. And you can actually enable interactions with other systems that are not natively private, like Ethereum and their applications. initiating these interactions from the shielded set via the bridges or via IBC. This is a way of feeding privacy to systems that do not support it natively in a more composable way. We're assuming that the users still prefer to go to these applications and this applies as well to app chains and then dApps on transparent chains. And the last thing is boosting privacy through UX. Here's another question. So there are 4 shield sets here, and then the difference is, actually the question is, which one do you think is harder, which transaction do you think is harder to link among all these 4? The main difference is that, so there are, so the size is different, the types of assets is different across the 4. And then there is another variable that we add, which is like the time in which they withdraw and the time and the amount that they withdraw. Which one do you think is hardest to generalize? You think it's B? B or D, did you say? Yeah. B. Okay, that is interesting. Uh-huh. Yeah, okay. So the answer I got here is B, which is shielded set size infinite and types of the asset 1. Okay, so one asset. Okay, so you actually think that having multiple assets in the set does not make it harder to okay, I get your point. But actually what I wanted to reflect in here is that there are things that you can do to improve just default practical privacy for the user. If you are on the interface level, randomizing, for example, the times of withdrawal, and then also the amounts that you're withdrawing for the asset. So these are some things that you can do to boost privacy through UX. And just a reminder is that we should actually focus on building privacy tech for everyone and not just for cypherpunks. And an approach tomorrow is one that relies more on an intent-centric architecture. So we're working on ANOMA, and then in this case, the main property that the protocol can provide to application developers and to the users is what we call information flow control. Information flow control is more about from the intent creation, which is the off-chain signed message, what data, giving the users the control of what data gets revealed at what point in the intent and transaction supply chain until it gets settled. If you're curious about this property, you can take a look at the repository of Taiga. And also Yulia gave a workshop yesterday about Taiga and information flow control and also private solving. That's the end of my talk. If you have any questions, happy to take them.